A little while back, I was working for a motor insurance company, and one of the insurances that they sold was to people that ride motorbikes. The graph you're seeing in front of you shows the frequency with which the drivers had accidents which injured third parties. On the x-axis, you have the age of the policyholder, and on the y-axis, you have the frequency of injury to third parties. What do we see? Well, at the very low ages, motorbike drivers are reckless, they have lots of accidents, or maybe they're just inexperienced, or maybe they're both reckless and inexperienced. There seems to be some kind of sweet spot around about the mid-30s, where accidents are low, and then over here we have what we call the midlife crisis, where it seems that people between the age of 40 and 50, I think they used to call them born-again bikers. Anyway, they get on the bikes, they have a bit of fun, and they have some accidents before people getting slightly older, and possibly that's a deteriorating frequency again. It's difficult to tell from the data. So, what's the difficulty with modeling this with a linear model? Well, we talked about it before. If y equals some intercept plus beta naught times the policyholder age, the only possible model we could fit would be some kind of straight line. I'm not quite sure what straight line it would fit. Maybe something like that, downward sloping all the way down. That's pretty hopeless. So what can we do? Well, we have learned that we can fit a polynomial model. How would that look? If we allowed a quadratic feature into our model, h squared, well, quadratic features tend to look something like that, so you could imagine we might somehow be able to fit that particular effect a little bit. The thing is, if we fit this effect over here with a quadratic, you're going to start getting negative frequencies right down there. It's going to be very difficult, so you'd probably need to add a cubic and many higher powers in order to fit this reasonably, which is a pain. As you start getting higher powers, the actual value in the h column gets huge. H to the power of 4 is going to be pretty big. It all gets a little bit tricky, and there is a much easier way. Imagine it was possible to build functions out of bits of straight line. We could build this function without too much difficulty. You would have a straight line over there, a straight line over there, maybe one over there, one over there, and one over there. With 5 bits of straight line, we could fit this function pretty accurately. So the question is, what features do we need to add into our data in order to fit bits of straight line? Well, what we're going to do is we're going to add to our data a new feature. So besides having age, we're also going to have a column which is the greater of 0 and age minus 35. What does that column look like? Well, if age was 20, this column will be 0. If age is 25, it'll be 0, all the way up to 35. And if it's 40, then this new feature will be 5. I've drawn them out here. You can see the original age column in red, and you can see the new feature down here in blue. What is the point of doing all that? Well, let's try and think it through together. Say we start off with a model which is the frequency of third-party injury, if you remember. Frequency of third-party injury equals minus 0.425 minus 0.01 times age. You're going to get a model looking something like this, where the frequency goes down. Well, if you remember, round about certainly at the age of 35, it didn't go down any further, it started going up. So we somehow need a way to make this line, for example, go flat from age of 35 onwards. We want this line to do that. Now, if you remember, the new feature which we created was 0 all the way up to age 30, and then it started going up. So all we need to do to make this flat effect is add 0.01 times that second feature we created. And here we have it. With these two features, the original age plus the new feature which we created, which was the greater of 0 and age minus 35, we are able to create this relationship, the decreasing relationship that we see in our data, and then a flat line after the age of 35. We can add more of these linear features. For example, we can add another one which has a kink at the age of 20, So adding some multiple of that allows us to flatten the line a little bit from age 20, and then have the other one that we had at age 30 maybe going slightly upwards, and you would end up with a model such as the one over here. I have a feeling that's a typo, and it should be a plus. Now, I don't know if I've explained this very well or if you're understanding it, but I'm just going to summarize. And that is, if you have a column in your data such as age, which takes different values, 20, 22, 24, 30, 35, 40, 45, I hope you'll agree that with just that feature in a linear model, it's impossible to create anything other than a global straight line all the way through age. If we want there to be local effects at different ages, where the frequency goes down at some ages, it goes up and down at other ages, we need to do something. We've talked about adding polynomial features like age squared and age cubed. That is a bit messy. It is possible to do that, but what we're going to look at here is add these other features, which are the maximum of 0 and age minus, for example, 20, and then something similar, for example, at age 30, another one at age 40. So this one over here will actually look like this. So we have a 15 there, 0, 2, 4, 10. This one over here. You end up with these new features, which are essentially flat bits followed by upward sloping straight lines, but from different points, from age 20, from age 30, from age 40. These points over here are called knots. I have to say, it doesn't matter too much if you don't understand how those features can turn themselves into lines of quite a flexible shape. So long as you're able to create those features and add them to a data set, your penalized regression is going to work. It's going to have the flexibility it needs to fit these local effects. You certainly don't need to worry about this page, but I'll read it through in any case. The kind of model that we have now says that the thing we're trying to predict, which in our case is frequency, but normally referred to as the target variable, is predicted by the sum of whatever the coefficients are times some function of age. You saw that the function of age we were using were these very simple kind of straight lines things which are flat and then start going up from a particular age, which we call a knot. In the Elements of Statistical Learning by Hastie and Tibshirani, they call these functions over here basis functions. That's not massively important as far as we're concerned, but it's just in case you come across that term, you know what it means. Now, I'm not quite sure if you can see this clearly enough, but what I've done is used loads and loads and loads of basis functions and put them through a linear regression, and the bluish line has completely captured the shape at every part of that curve. Now, what do you think about that blue line? Is it a good fit? Is it a good model? Well, it's an amazing fit to the training data, but it's probably a very bad model because it is overfitted to the data. Look at that little bit over here where the blue line goes up and down. Likewise over there, it's just reacting to the noise in the data. We need some way to regularize or to penalize this model so that it only uses as many splines as it needs to predict well over data that it hasn't seen before. How are we going to do that? Well, you should not be surprised that all we need to do is put a load of these splines through a penalized regression. The penalized regression will fit the model on train, it will test it on validation, and it will keep on reducing the coefficients for the splines that don't add value to the model until either, if we're using ridge regression, those coefficients are very small, or if we're using the lasso, those coefficients are set to 0. And here's an example of a model which was fit using penalized regression. I made a bit of a mistake over there. You can kind of ignore this bit, but you can see that over the rest of the shape is actually done really well to smoothly go through most of the data points. If you go back far enough, people that fitted models would probably have done this smoothing by eye, but here it's all been done by the penalized regression and done in such a way that it optimizes performance on data the model has never seen before. Now, I have to say, I've explained this in the past 2 years to students sitting in front of me in the lecture hall, and by the time I got here, there were a load of blank looks. So if you're looking blankly at the screen now and thinking, what on earth is he talking about? You're not alone. What can we do to try and dispel this confusion? I think the best way is, although I haven't done it yet, to try and go back to our polynomial regression and create some simple splines there, some simple linear splines there, and see how they go about fitting the data. So let's give that a go.